Processing long visual context in vision language models is computationally bottlenecked and highly prone to distraction. While models are increasingly capable of handling hour-long videos or massive image collections, processing all these visual tokens at once is computationally infeasible due to GPU memory limits. Moreover, as the number of distractor images grows, model performance degrades significantly. To solve this, we need an efficient way to retrieve only the most relevant visual frames before generating an answer. ReToken introduces a lightweight, single-token solution that dramatically improves visual retrieval. Standard attention scores inside pre-trained vision language models are highly unreliable for retrieving relevant visual frames. You might think we can use the model's own attention scores to find relevant frames, but research shows this fails. First, attention in VLMs is trained for next token prediction, not retrieval, meaning high attention tokens do not always correspond to query-relevant content. Second, typical training data features fully relevant images, so the model never learns to select among distractors. As shown here, attention scores fail to distinguish ground truth frames from distractors, resulting in poor recall. The key breakthrough of this paper is the discovery of a striking asymmetry between key and value projections. In a transformer, value projections carry the actual content propagated through attention, making them highly sensitive to semantic meaning. By matching a precise target phrase against the average visual value projections rather than keys, retrieval recall jumps significantly. However, simply averaging all question tokens introduces noise. To exploit this rich value space, we need a precise, learnable target that can extract the exact visual features we need. ReToken introduces a single learnable embedding trained explicitly as a retrieval target in the value space. During training, the VLM remains completely frozen. ReToken scores each visual frame by computing the cosine similarity between its projected embedding and the frame's mean value vector at the final layer. This lightweight design adds virtually zero parameters, consisting only of the token embedding and a single projection matrix. This makes it incredibly easy to train on a single GPU using a class-balanced binary cross-entropy loss. At test time, ReToken operates via a highly efficient two-pass retrieve-then-answer pipeline. In the first step, the video is processed once, and its visual key-value features are saved in a persistent cache. In the second step, when a question is asked, the first pass appends the ReToken to compute retrieval scores and select the top K relevant frames. The second pass then runs standard generation, attending only to the cached features of those selected frames. This avoids expensive video re-encoding and saves massive compute. Despite being trained only on a small multi-image question-answering dataset, ReToken delivers massive performance gains. On the Visual Haystacks benchmark, it improves Qwen3VL by over 13 points, retaining most of the Oracle upper bound accuracy. More impressively, it transfers zero-shot to extreme long video understanding. On LVBench, where videos average over an hour long, ReToken yields an 8-point improvement, outperforming much heavier models while fitting entirely on a single H100 GPU. While highly effective, ReToken has a few key limitations. Because it scores each frame independently, it struggles on tasks like video summarization where evidence is dispersed across the entire video rather than localized. In these cases, uniform frame sampling actually performs better. Additionally, the two-pass pipeline introduces a small latency overhead during the retrieval phase, and the model currently cannot capture complex temporal relationships that emerge only from combinations of consecutive frames. In conclusion, ReToken represents a major step forward for efficient long-context multimodal reasoning. By revealing that the value space is the true home of semantic alignment in VLMs, this research opens up new avenues for lightweight retrieval. Future work will focus on retrieving sequences of consecutive frames to capture temporal dynamics and scaling ReToken to even larger video datasets. This simple, single-token addition proves you do not need massive compute to solve long-context visual understanding.